Great. Welcome everyone to another week of GROOT. So today we'll be hearing from Wenwen Li about configuration spaces of metric graphs with restraint parameters. So take it away, Wenwen.
Thank you for inviting me. So today I'm going to talk about the configuration space of robots moving on graphs. So, okay, now it works. So so the traditional way is we treat each robot as a point. So we have two assumptions. So we assume the length of the rail is finite. So this is pretty realistic, right? So we couldn't have like infinite length of rails like in real life. And second, because those robots, they're really expensive, so we don't want them to collide with each other. So therefore, we assume the two robots, they cannot be placed at the same spot. So here is an example. So, so this is actually an arrangement of two robots on this interval-shaped rail. So this red thing is the rail, and we have two robots, and they're distinct. Okay. So let's actually write it out. This, or should I say, like the inequality system to describe this situation. So if we assume the length of the interval is 1, and we have this orientation from the left to right, and so we let x to be the distance. So the distance between this purple robot and the length of this interval to be x, and let y to be the distance between the the green robot and the length of this interval to be y. And we actually can translate this figure into an inequality system. So for this specific arrangement, we have, x is in between 0 and 1, and y is in between 0 and 1. So in this case, x is actually strictly less than y. And there's a like dual arrangement for this one. If you switch those two, so if you switch the position of those two robots, so they will have the other way, so y is less than x. And then if you combine those two inequality systems to one, we obtain this inequality system. So x and y, they're all in between 0 and 1, and x does not equal to y. And we can actually draw the solution space of this inequality system in R2. And on the right-hand side, this figure actually is the solution space. So basically, as you can see, so we have a square, and we remove the main diagonal from the square. And each point in this solution space represent an arrangement of those two robots on this interval-shaped rail. Okay, and we can do this for arbitrary topological space X. So basically, so we call this space the second configuration space of a topological space X to be a collection of ordered pairs lives in this product space X plus X, such that X does not equal Y. Okay, and we think the second configuration space of X as a collection of all such configurations of two distinct robots in X. And I mean, so the thing we just draw is the second configuration space of the unit interval 0, 1. Okay. Oh, by the way, so if you have any questions, just feel free to interrupt me. Okay. And let's do another example. So if the underlying space is the Y-shaped graph, then this figure is the second configuration space of the Y-shaped graph. So in this graph, we have let's see, 6 squares actually, and we have 6 red triangles. So we call those triangles fins, and we remove the center point from the figure, and we also remove the hypotenuse of each red triangles. So basically, so those points represent that we place those two robots at the same spot on the graph. So we have to remove them. And so, okay, so you already, so you might already feel that, so the second configuration space of a topological space might really complicated because the underlying graph, the Y-shaped graph, is actually homotop equivalent to the unit interval, but they really have the different second configuration space. Okay, so similarly, so we can define the nth configuration space of the topological space X as the collection of n tuples. So now those n tuples lives in the product space X to the n, such that for each pair, xi does not equal to xj. For if I does not equal to j. And so so we're topologists. So we want to know the topology for this space. So this space actually has the subspace topology inherited from the product space. Okay. However, so in the real life, so we can't treat robot as points, right? So so we know the Roomba, so vacuum cleaner. So there are like thick particles, right? So we can't treat them as points, and this motivates us to use the other definition, so which is the nth configuration space with restraint parameter R. So let's just start over. So we think endpoints xi, so x1 to xn lives in a metric space x delta. So delta is the metric, such that the distance between xi and xj is greater than or equals to a certain value rij. Okay, so now the nth configuration space with this restraint parameter R is the collection of n tuples. So again, so this n tuple lives in the product space, such that we have, so the minimal distance between each pair of points is greater than or equals to the given value. Okay, and so in this talk, we actually focus on the case that n equals to 2, meaning that we only have two robots on the rail. And X is the geometric realization of a finite graph. Okay, so before we dive into the theory, so let's just go through the definition a little bit. So this is just like a reminder. So a graph is a tuple consists of two sets, V and E, where V is a set of vertices and E is the set of edges satisfy this given condition. So this means that so every edge of the graph is either one or two element subset of the vertex set V. Okay, so here, so a graph is a purely combinatorial object, and the geometric realization of a graph gamma, defined by this weird symbol here, is a topological space consists of the following. So we have points that represent the vertices of the graph, and we have the line segment represent the edges of the graph. And below, so this figure, which we're gonna use in the later part of my talk, is called a star graph. So actually, so you see there's a little K in a superscript. So it represents that, so this graph, it has one center vertex, it has K leaves or K petals. So basically, so this is the K represent. So in particular, the Y graph is actually the star 3 graph. Okay, so far so good. Okay, cool. So let's move on. Yeah. So now so given a vector L lives in this space, we call the topological space X. So here, so X is the geometric realization of some graph. Okay, so X is called a metric graph if we assign a positive number for each edge of the graph. So this LE is the length of the edge E. And now, so this X, so it naturally has like a so it naturally has like a metric called the path metric delta, meaning that for every pair of points xy lives in X, the delta of xy is the length of the shortest path from X to Y. And we use this notation X sub L to represent this metric space. And then, so here I just rewrite the definition of second configuring space with this restraint parameter R and edge length vector L to be, again, the collection of ordered pairs, because now we only care, so we only have two like robots on our graph. So the second configuring space of this metric graph X with restraint parameter R and edge length vector L is the collection of pairs, ordered pairs, X, Y, such that the distance between X and Y is greater than or equals to R. Again, so R is the minimal distance allowed between those two robots on the graph. So just for the sake of simplicity, when L is fixed, we just get rid of this subscript L from this, like from the bottom. So we use X to R to represent this space. And like one cool fact is that when R is small, this restricted configuring space, X to R is actually homotopy equivalent to the second configuring space of X. So they're actually, so they have some relation when R is small. Okay, so let's move on. Yeah, so let's just do one example because we just have like lots of definitions. So now, so let Y be the metric graph with the shape Y, but we want to understand, so we want to understand like the metric on this graph. So for this example, so the metric we have here is actually, let's see, so the length of edge E2 and the length of edge E3, is 1. Okay, but the length of edge E1 varies. Okay, and so we call this configuring space by this notation Y2 sub R and L, and let's choose different values of L, basically different edge length of E1, and we vary the value of R and to see what happens. Okay. So let's see which number I choose first. So let's choose the edge, the length of edge E1 to be 1. Okay. Oh, okay. So before that, I have one more slide. Okay. So we use the following inequality system to describe the configuring space. So for this one, for the first inequality system, so this describe the scenario that those two robots, they're actually on different edges of the Y-shaped graph. And for the inequality system 2 and inequality system 3, so those two inequality systems characterize the scenario that those two robots actually on the same edge of the Y-shaped graph. Okay. Yeah. So let's move on. So now, okay, so here, so we assume that the length of the edge E1 is 1. And now we vary the value of R. Again, R represents the minimal distance between those two robots, okay? So when R equals to 2, the configuration space of this Y-shaped graph consists of 6 points. Okay, and on the left-hand side, so I haven't defined it yet, but right now, so we just think about this as like a bookkeeping of the path components of this topological space. Okay, so when R equals 2, because we have 6 path components, so therefore on the left, I draw 6 dots at R equals to 2. Okay, now let's decrease the minimum. So now let's decrease the minimum value allowed between those two robots. So when R equals to 1.7, so the space consists of 6 triangles. Okay, because we still have 6 path components, so therefore we draw like a ray from R equals to 2 to R equals to 1.7. And now let's further decrease the value of R. So when R equals to 1.3, we have, so we still have 6 path components, but so as you can tell, so each triangle get larger. And when R equals to 1, now suddenly, so we only have 1 path component because, so space is path connected. So therefore, on the left-hand side, so we kill 5 of the 6 path component here, and we only keep this one alive. Okay. Now, if we further decrease the value of R, the hole gets smaller, and we have 6 yellow triangles here. And when we further decrease R, the hole gets smaller and the triangles gets larger. But I mean, so we still have one path component, so we just keep drawing the ray. And when R equals to 0.2, the hole gets like even smaller and triangles get larger. Okay. So at the end, so here's the summary. So when the length of edge U1 is 1, we have the following summary. So the homotopy type of this configuration space, when R is greater than 0 and less than or equals to 1, the homotopy type is actually S1. And when R is greater than 1 and less than or equals to 2, the space is homotopy equivalent to the space consisting of 6 points. Okay. So yeah, so let's try another value of the length of edge U1. So how about we choose 2 instead of 1? And let's see what happens. So when R equals to 3, we have, so the space actually consists of 4 points. So we draw 4 points at R equals to 3 on the left. And when R equals to 0.5, so we have a space that consists of 4 triangles. And again, so we still have 4 path components. So therefore, on the left, we draw rays, from R equals to 3, basically. And now when R equals to 2, so we have something like interesting happen, right? So first of all, those 2 triangles, they merge into 1 path component, and similar for those 2. So we killed 2 of the 4 path component right here, okay? And moreover, we have 2 more points in this space. So therefore, we add 2 points represent these 2 path component born at R equals to 2. And when R equals to 1.7, so the right hand side is the configuration space. And so as you can see, we have larger triangles here. Yeah, we even have 2 new triangles right here. And when R equals to 1, this space become path connected. So therefore, so we kill 3 of the 4 path component at R equals to 1. I only keep 1, 1 path component here. And when we further decrease R, so the space going like this. So this is, so this space is the configuration space when R equals to 0.2. And here's the summary. So this configuration space is homotopy equivalent to S1 when R is greater than 0 and less than or equals to 1. And the space is homotopy equivalent to the space of 4 points when R is greater than or equals to 1 and less than or equals to 3. But however, so as you can tell, those 4 points, they're actually different. So they're not the same, 4 points. And this is something interesting that we can actually read it from the figure we draw on the left. Okay. So yeah, so here's the general way to characterize the cell for the second configuration space of a metric graph X with the restraint parameter R. So so basically we have 2 scenarios. The first scenario is that those 2 robots are actually on the same edge, and we use this inequality system to characterize this situation. And if you draw this inequality system on R2, you will obtain a green shaded area like this. Okay, so if you increase R, so what will happen? So if you increase R, those 2 parallel lines, they will get closer to each other. Okay. Yeah, so this is one scenario. The other scenario is those 2 robots, they're actually on different edges. And you can, so basically you can write out an equal system to characterize this situation as well. And if you draw the inequality system actually on the R2, the green shaded area is the solution space of that inequality system, and this is a cell of the second configuration space of the metric graph X. And yeah, and so if we increase the value of R, the two parallel lines, so with the positive slope, they get closer to each other, and so is those two parallel lines with negative slope, they get closer to each other. So basically, so when we change the value of R, so the shape of the cell might change, and the homotopy type or the homeomorphism type of the entire space might change. And we want understand that as well. So yeah, so let's actually run into the question I'm gonna solve. So we want to understand how does this restricted configuration space, so in particular, the homology groups of those configuration space change when we change the value of R or the space varies. Okay, and so to understand so to solve this question, so a natural tool to use is called the persistence homology. Yeah, so I think there's a speaker already to talk about the persistent homology, but here just like a brief review. So here, so let F be a field and P is a partially ordered set. So a persistent module over this poset P is a family of vector spaces over the field F, and a doubly indexed family of linear maps, such that for any comparable triples S less than or equals to T less than or equals to U lives in this partially ordered set, the composition of them, rho ST and rho TU, equals to the map rho SU. And also, so we require rho SS to be the identity map at MS for all S in this poset P. So in other words, a persistent module is a functor from the poset P treated as a category to the category of vector spaces over the field F. Okay, and so in our setup, this means so the partially ordered set we have is the opposite category of the of this R. So again, so we treat R as a partially ordered set, and so this is the so this is a composition map actually. So we have so the S homology group of X2S to S homology group of X2T. So here T is less than or equals to S. So we have the opposite category thing here. So far so good. So I couldn't see all your faces. Okay, so let's move on. Oh, someone has a question. Oh,
sorry, it was a mistake. Sorry.
Okay, cool. Okay, let me see the time. Yeah. So in 2012, Crowley-Bovee approved this pretty technical theorem. So he proved that any pointwise finite dimensional persistent module is isomorphic to a direct sum of interval modules. Okay, so I haven't defined this yet, but the point is that this theorem tells us the interval modules, they are building blocks for the pointwise finite dimensional persistent modules. And because of the theorem, so we know we can associate a barcode to a finite dimensional pointwise finite dimensional persistent module. And let's go back to this example here. So this means the thing we draw at the beginning is the barcode for the zeroth persistent module of this configuration space. Okay, similarly for the other one. So this figure here is the barcode for the zeroth persistent homology of this configuration space. Okay, so far we only have one parameter, but what if we consider 2 parameters instead of 1 parameter. So the question becomes to how does this homology group of the configuration space change when those 2 parameters vary? Okay. So here's a remark. So it turns out this problem is impossible to solve. So even we are, even we are dealing with like Z2, so like the discrete version of R2. So this problem is still like impossible to solve because we have this like equivalence of categories, and we know because fxy is not a PID, so therefore there's no hope to classify the finally generated modules like in this category. So therefore we have 0 hope to solve the classification problems in the so in this category. So which is the 2-parameter persistent module category. So we have no hope. So in other words, we have to calculate the indecomposables like in this category 1 by 1. Okay. And yeah, so let's go back to this toy example we did earlier. So as you can see, we have a new figure on the right. So let's translate this figure a little bit. So for each line, so we call the lines like hyperplanes. Basically, for each point on the hyperplane, so it represents a parameter such that the homotopy type or homomorphism type changes when we move from right to left, or from bottom to the top. So when we go this way, so the homotopy type or the homomorphism type might change. But within this region, so the homomorphism type doesn't change. So therefore, we can actually calculate like the homomorphism type region by region. Okay, and this is what we did. So yeah, so we calculate the homomorphism type for each region. So for example, so the yellow region here, so this means every parameter lives in here. It represents so it represents a second configuration space with that parameter, and that space is homotopy equivalent to the space of 6 points. Okay, similar for the other region, like for the gray region, as you can see. So for every like point live here, so it represents a second configuration space with that given parameter, and that configuration space is actually homotopy equivalent to space of 4 points. And now, so basically, so this figure gives us a filtered topological space, and so if we apply the homology functor, we will get the persistent module. And this is what we did. So for this one, so we apply the zeros homology functor to the filter space. So we obtain the zeros persistence module of this configuration space. Okay. And similarly, if we apply the first homology group functor, we'll get the first persistence module, so the first persistent homology of this configuration space. And so the figure on the right actually tells us this module is, so first of all, is so pH1 of this configuration space is, should I say, is interval. So it's an interval module, basically. So it means the support of this module is an interval in that whole set. And because it's a thin module, meaning that so we only have 1 copies of F for each like point in this region. So this means pH1 is an interval module, and we know the interval modules, they are indecomposable. So therefore, pH1 of this Y-shaped graph is with two robots is interval decomposable. Basically, that's the story. And we want to do a similar thing for pH 0. In other words, we want to figure out the indecomposables of pH 0 of this configuration space. And so here's what we did. So basically, so we construct another module coming from this pH 0 as following. So for each chamber, so we associate a vertex to each chamber. And if there's a wall in between two chambers, we give so we give an arrow between those two vertices in the other graph. So yeah, so as I can see here, so this diagram on the right is the new persistent module we created from the given one. Okay. And so so the point is we find the indecomposables of this new persistent module and we translate back to the original ones. And here's what we did. So I will come back to this later, but I do want to show you like what we did here. So so this is the indecomposable direct summon of pH 0 of this configuration space. So immediately, so you can see because we have two here. Okay, so the number here represent the rank or I mean here because it's the so they're all like vector spaces. So it represents the dimension of the vector spaces for each point in this region. So basically, so first figure already tells us pH 0 is not interval decomposable because we have those two here. But however, so the other indecomposable direct summon of this persistent module, they're actually they're just like interval modules. So as a corollary, pH 0 of this persistent module is not interval decomposable. So so basically, so this space is simple enough, but the zeros persistent homology of this configuration space is already pretty interesting, right? So it's not like interval decomposable anymore. And so the idea behind this is, so we find a factorization from so originally, so this persistent module is a functor from this poset to the category of vector spaces over the field F. So we find a factorization of that functor by the following. So we factor through the functor through this new functor F, and the other one is from this poset P we constructed to the category of vector space over field F. So yeah. So this is pretty neat. So I really like this result. And this simplify our calculation because so this new this new persistent module actually, so it's not like a dense object, right? So it's a like discrete object. So so once you figure out the indecomposables of this new representation, we can actually translate back to the old ones. And get the like the indecomposables direct summon. Okay, so so this is for a Y-shaped graph. Can we do a similar thing for like the star graph? So actually we can. Okay, so let's keep that for now. So yeah, so we do the similar calculation for the star graph as well. So here k is greater than or equal to 4. Okay. And yeah, so here, so the point is, so we assume the length of the edge of, so the edge of the star graph, except the edge E1 is 1. So basically, so we fix the length of the other edges, but E1. So we change the length of edge E1 for this graph. And the cool observation is this, so the second configuration space of this star graph, so it has the same critical hyperpoints as, the second configuration space of the Y-shaped graph. So this is super cool, and this simplify our calculation as well. So we just do the similar thing. So we calculate homomorphism type of each region, and we apply the homology functor. And this is what we got. So on the left, this is the zeros persistent module, corresponding to the second covariance space of the star graph. And this is what we got. And so the figure on the right is the first persistent module, corresponding to the star graph with 2 robots. Okay, so the figure on the right actually tells us pH1 of this pH1 of this space is again like interval decomposable, because this is an interval in R2. And here's a remark. So the similar result holds for pH 0 and pH 1 with integer coefficients. So we will have same number for each region, but the number will represent the rank of the homology group. So let's move on. So we did a similar thing. So now we have the persistent module, and we want to understand the building blocks. So in other words, the indecomposable direct summon of pH 0. Okay, and this is what we got. So we calculate the incomposable direct summon, so basically, the first figure we got here is an indecomposable direct summon, because we have those two for those two regions. So this represents that for each point we assign an F2. So in this representation, so therefore pH 0 is not interval decomposable. Okay. Let's see what we did. Let's see what time. Yeah, I think I still have time. So let me show you the other space we calculated. So we also did the H graph. So so H graph, so in some sense, so you can generate it from the star graph by concatenate like a leaf of 2 star graphs. And so basically, so we proved that when the underlying graph is a tree, the homology group of the second covariance space of that space is 0, and the first homology group of that covariance space is always torsion free. So let me just show you the thing we calculated. So so when the excellence factor is this, meaning that the length of edge E2 or to the edge the length of edge EM is 1, and so is this side, and we change the edge length of E1, which is the bridge. Okay. So when we have that edge length vector, then so the figure on the left is the zeroth persistent homology of this space. And the figure on the right is the first persistent homology of this space. So we calculate this, and so we also proved that the pH1 is interval decomposable, because so this is actually an interval in this pole set. So this is R, so the opposite category of R cross R. So again, this is like a weird shaped like interval, but I mean, so it is like an interval. So in that partially ordered set. However, so we want to understand the building blocks of pH 0 as well. So it turns out the pH 0 of the second configuration space of the H graph is interval decomposable. So so basically, so you can see like every region has dimension 1. So this is like fantastic, right? So we have like a like star graph, and so the zeroth persistent homology of the second configuration space of star graph is not interval decomposable. However, like like somehow like a little bit more complicated like space, which is the H graph. So zeroth persistent homology group of that space is actually like interval decomposable. Yeah, and so okay, so this is for H graph, but like for generalized H graph, we have a similar like result here. And I didn't draw. It's a little bit complicated, but again, so the peer zero of the generalized H graph is also interval decomposable. Yeah, I think I should just stop here and let me know if you have any questions.
Cool, great. Let's maybe give the speaker a quick round of applause. Lots of clapping emojis in the chat as usual. Yeah, so yeah, if anyone has any questions, please feel free to ask. I do sort of have one. I don't know how to formulate it quite precisely yet, but so let's say this, going back to the example of the star-shaped graph, where you have these different edge lengths, and maybe let's assume for a second that all of the edge lengths are integral. So you just have integers for those. What do you expect would happen if you varied those edge lengths, to different integers? Like if you move E1 from being length 1 to length 2 to length 3.
Yeah, so that's actually like a really good question. So the point is like for the other so for example, like for edge E2, so the edge length is fixed. Okay. So if you choose a different value, like for example, if you choose the edge length of E2 to be 2 instead of 1, so one way to solve this is you use Mayer-Torres spectral sequence or Mayer-Torres like long exact sequence. So basically, so you have like two covers of the graph, and so you calculate like the covers, so the homology of the covers separately, and you calculate the homology of the intersect of the covers as well, and you can like get like the homology of the like ambient space, like using that like argument. So basically, so for this specific value, it's like the building block for the other graphs, basically.
Do you expect to get like a totally different, for these diagrams where you had kind of like R2 partitioned up into these different regions based on the like ranks of the vector spaces you get there? Do you expect that to like vary significantly if you change these? Like you imagine you have K edge lengths, so you're in Z to the K and you're moving around in Z to the K,
Let's see. So it might change because so the minimal distance between two two robots, they're so the values they varies, right? So if you if the edge length of E2 is super long, then the space might get connected actually for larger R. So basically, so the homotopy type of the underlying graph, so the homotopy type of the underlying graph does not does not like imply the second configuration space of the graph. So basically, so the configuration space of a graph contains more like information than the homotopy type of the underlying graphs.
Thank you. Yeah. I did have one question about a generalization, but it's kind of hard to describe. So you went from star-shaped to the H-shaped. And
yes.
Like you think of the H-shaped as like two star-shaped glued together along one
common edge.
Yes.
Yep.
Yeah.
Yep.
Can you do that for like multiple? Now, if you want to start
Yes.
gluing on other star-shaped things.
Yes, of course. And so actually, so the H graph and the star graph, they're like building blocks for trees. Yeah. So basically, so if you subdivide trees, you will get like some star graph and some H graphs. Yeah. So once we know so once we know the information about the like the 0th persistent homology of the star graph and the 0th persistent homology of the H graph, we can actually get you know, like the zeros persistent homology of the tree graph. So once we know like what does the tree look like, so we just glue them together like in some way, then we'll get, you know, like the solution.
Yep. Oh, let me check chat just to see somebody posted in there. Okay, just a lot of thank yous and great presentation and so on and so forth. So okay, let's maybe thank the speaker once more. So
yeah, thanks.
And I will stop the recording.